All right, so we've been working with these exponential relationships for a while now, and we now know three ways of writing down the same thing, three different ways of expressing a relationship. The first you knew before you even came to me, probably, which is I can say something like 10 to the third power, well, is 1,000. It's 10 times 10 times 10, right? All right, so we've been working on these exponential relationships for a while now, and you now know three different ways of writing down the same information. So three different ways of expressing the same mathematical relationship, I should say. The first you knew before you ever got to me, and it was something like, well, if I say 10 to the third power, that's equal to 1,000, right? It's 10 times 10 is 100 times 10 is 1,000. It times itself three times. And then we introduced this idea of the root, so the cube root. I'm going to write this one two different ways. So the cube root of 1,000 is the same as 1,000 to the 1/3 power, which is 10, right? So that's the second way, is this idea of roots. So the root spits out the base. And then the last way is the newest way, and this is the least familiar to you. Log base 10 of 1,000, and this of course spits out the exponent, is 3. So these all mean the same thing. They express the same information, right? The 10 to the third power is 1,000, but they're written different ways with different notations. So we're going to dive in here to some properties of these relationships, and I'm trying really hard not to do what was done to me when I was learning these relationships in high school, which is just they made me memorize a bunch of rules, and I didn't really understand why the rules were the rules, and I of course immediately forgot them once I graduated. So that my goal is for that not to happen to you guys. So I want to start with a little bit of a motivation here of like why these rules work and the types of transformations that we're using these rules for. So I have these graphs here in your notes that are graphs obviously of COVID cases right at the very beginning of the pandemic in 2020. They're COVID cases outside of mainland China, as you can see. And I've presented this information two different ways. And what I want you to do is pay attention over here to the scale of each graph. So notice we're counting by 5,000 in one graph. And then here the scale on the right-hand graph is a little bit different. So that's the interesting one that I want you to pay attention to. So notice the scale goes from 10 to 100 to 1,000 to 10,000, right? So that is not a linear scale like we're used to. This is called a log scale graph. And notice what it does to our data, right? So we've talked before about how COVID spreads exponentially. That's why we're interested in exponential growth, or one of the reasons. So we have this curve that gets steeper as time goes on. And we don't think like that, right? We think mostly in linear terms. And if I want to predict where this curve is going to go, it's kind of hard, right? So it's kind of hard to see exactly where to put that next dot. But if I plot it on a log scale, where my scale increases by powers of 10 here, notice what I get is basically a straight line through all those points. So we often present data this way when we're dealing with real life phenomenon, especially when that phenomenon increases at an increasing rate, right? So here is this main idea I want you to keep in mind as we talk about these rules. The main idea is that when we take a logarithm, or when we use one of these logarithmic scales, we transform a multiplicative relationship, one that's hard to wrap our brain around, into an additive relationship, so one that's a little bit easier for us to think about. So here's an example of how this is used in real life. So net worth of U.S. households. Notice the scale here. It starts at 1,000, goes to 10,000, then 100,000. Because this is something that grows exponentially. It grows as a percentage base, not a linear base. So this is an easier way to represent this information. This part where we're going down, by the way, is about right around the time I graduated college and started looking for a job. So that's one example of where we use this, and here is a really cool example. This is an image of the universe. Notice we're at the center. This is not how the universe is actually laid out, but this is a way of representing the whole thing. So as I move out from the sun, distance from the sun is increasing exponentially, but represented linearly. So from here to here might be, 1,000 times further than just from here to here. So space is like mind-bogglingly large, and one of the ways we can represent it in a way that our minds can literally like process it is using logarithms. Okay, so here comes the nitty-gritty. These are pretty easy to remember if you keep in mind the context that we just used. And these relate really closely to the exponents rules you already know, so I've included those here as well. Multiplication under this log transformation is the same as addition of two logarithms. So those two things go together, and then it makes sense then that division and subtraction would be related in that same way. And then here, power to a power, right? So exponents under this transformation become multiplication. So let's look at how these rules work very basically. The way we're going to practice them and build up our intuition is just solving equations here. So the way we use these rules is to rewrite our equations in ways that make them easier to solve. So for example, here I have two logs being subtracted, and by this rule here, that means I can rewrite that as one log with the insides being divided. So that's going to look like this, log base 2 of 9x over 9 on the inside. And then I didn't change the equation, right? So it's still equal to 1. So I've used this rule now to rewrite my equations. And then, well, I can obviously cancel my 9's here. And then I have log base 2 of x equal to 1. And then I need to take an inverse to isolate x. So what's being done to x? Well, it's a log base 2. So the inverse of that, and here's maybe the new thing for you, is raising both sides to the power of 2. So I get something like this, and you probably won't show this step as you work through these once you get comfortable. So log 2 to the log base 2 of x equals 2 to the first power. So this is an exponent here, and these operations cancel out just like addition and subtraction. So I get 2 left over here. So my next example is an exponential equation, and we're going to take a logarithm to solve this. But before we do that, we're going to get what's called a common base. So notice I have an 8 on one side as my base and a 2 on the other. What I mean by common base is that I want them both to be the same, so that I can take a log base 2, in this case, of both sides. So I'm going to rewrite the right-hand side in kind of a clever way. So I'm going to say 8, well, that's equal to 2 to the third power to the fifth power. And then I did not change the left-hand side. So notice this time I used one of my exponential rules to rewrite the right-hand side in kind of a common way. And then I can use that same rule, right, to say, well, this is 2 to the 15th power, because I'm multiplying my exponents, equal to 2 to the x plus 3 power. And then, well, if I have a like base and my two sides are equal, I can just say x plus 3 equals 15. It makes sense that those two things would have to be equal, right? I'm also, you can think of it as I'm taking a log base 2 of both sides. X, of course, is 12 here. So again, the goal here is to build up these intuitions about these relationships. And remember, the best way to do that is to keep in mind that this is a transformation, and that will make it easier for you to remember your rules here.